We're going to begin section 8.3 where we discuss parametric equations. We're going to start with a little background information about parametric equations because this is a concept that many of us are not that familiar with. So let's begin with a definition. Many curves are defined in terms of a variable called a parameter, which is a variable that's different from those representing the coordinates. So in the graph shown on the screen, what we have is a situation where someone kicks a ball. All right, and so when they kick the ball starts here. This is the point where it's kicked. Its path is that it goes up for a while and then it starts to go down. And so if you look at that and you think about coordinates, all right, so if we think about this point right here, we have an x value, which is going to denote the distance that the ball is at that point from the point that we kicked. So how far away is it? And we also have a y value, which is going to denote the height of the ball. And so those are our typical variables, x and y. If we have an additional variable, that is what we're talking about when we talk about a parameter. And so you can see that we have marked off along this graph, we have t values, which represent the time. So not only does the graph show an x and y value, which shows the horizontal and the vertical distance, the graph also reflects the parameter time and tells us where the ball is at a certain point in time. So what we're going to be looking at in this section is how to write these equations to represent this object's travel. So I'm going to go ahead and give you two basic formulas that we're going to be using. Okay, and these two formulas, while they look quite complicated, are actually not that bad as we start looking at some problems. And so our first formula is for the y value, and it says y is equal to negative 1/2 g times t squared plus v sub 0 sine theta times t plus h sub 0. And then we have a formula for the x. X is equal to v sub 0 cosine theta times t. And these parametric equations define the path of an object's travel. So what we're going to do is we're going to look at these two formulas in relationship to a problem. So our first example says that suppose a baseball is hit 3 feet above the ground and that it leaves the bat at a speed of 100 miles an hour at an angle of 20 degrees from the horizontal. Construct a set of parametric equations. Therefore, it's asking me to do an x equation and a y equation that describe the ball's flight and sketch a graph of the ball's travel. So we're going to look first at calculating our parametric equation for the y. So I have our equation written down. Y is equal to negative 1/2 g times t squared plus v sub 0 times sine theta times t plus h sub 0. Recall that g is the acceleration due to gravity, which is a constant value of 32 feet per second squared. Because we're going to use this in our formula, we need to be sure that every value that we plug into our formula has the same units, either feet or second. And so let's look at what we know. We know that the h sub 0 is the initial height, the height at time 0. And so we know that our baseball was hit 3 feet above the ground. So h sub 0 is equal to 3. We know that our initial velocity, which is the v sub 0, is 100 miles an hour. We're told that the ball leaves the bat at a speed of 100 miles per hour. So if I'm thinking about my units, the 3 feet on the h sub 0 is fine because it's going to match up with the feet in the 32 feet per second squared. The 100 miles per hour has got to be converted to feet per second. And so let's do that first. So I'm going to take my 100 miles per hour. And we're going to start converting. So I'm going to multiply first this 100 miles over 1 hour by 5,280 feet over 1 mile. Now keep in mind, when you do the conversion, what you want to do is you want to have something in fraction form here where the top is equal to the bottom. And so we know that 1 mile is equal to 5,280 feet. We also want to have it set up in such a way that our miles are going to cancel out. So if the mile is on the top over here, we need the mile on the bottom here. Now we need to take care of the hours, converting that to seconds. So I'm now going to multiply by, I'm going to put 1 hour on the top. Again, that's going to allow this hour and this hour to cancel out. And we're going to put seconds on the bottom because that's the unit that we want to bring in. So we know that there are 60 minutes in an hour and there are 60 seconds in each minute. And so that means that there are 3,600 seconds in an hour. Okay, so we're going to multiply. So on the top, we're going to have 100 times 5280 times 1, which is going to give me 528,000. And on the bottom, we're going to have 1 times 3,600, which is just going to give me 3,600. And so when I divide that, I'm going to get 146 point, we'll just go 1 decimal place, so 146.7. Okay, now let's look at what's happened to our units. The miles have canceled out. The hours have canceled out. And so my units that are left are feet per second. Okay, so I know that that is my V sub 0. That is what I'm going to use to plug into my formula for V sub 0. All right, so let's go ahead and let's see what we've got when we start plugging numbers in. All right, so I have y is equal to -1/2. I'm going to put the g value in at 32. Okay, I'm going to leave the t. T is the time, and that's going to change as this baseball moves throughout the air. So that is a changing variable. We'll leave that in. I'm going to put in my V sub 0, which we found to be 146.7 sine. Now, what is our angle? If I look back at my problem, remember that the angle was 20 degrees. So we're going to plug that in. Again, we're going to leave the t, and we're going to put in 3 for the initial height. All right, so let's see what we can do to simplify. So 1/2 of 32 is going to be -16. I'm going to come down here with it. So I've got -16 t squared plus, I'm going to go to my calculator with the 146.7 times sine 20. I'm going to get 50.2. Again, we're going to go 1 decimal place on these, just as the book does. So 50.2 t plus 3. So now we have the parametric equation for y. Okay, so let's go ahead now and calculate our parametric equation for the x. So we have our basic formula, x is equal to V sub 0 cosine theta times t. And so I'm going to use the same values. I'm going to plug in the same number that we came up with for V sub 0, which was 146.7. I'm going to do my angle at 20 degrees. And I'm going to multiply that by t. So this one is a little easier to work with. So we're going to have 146.7 times cosine 20 gives me 137.9 t. And this is my other parametric equation to describe that object's motion. Okay, so we've constructed this set of parametric equations. Now we need to sketch a graph of the ball's travel. And so we're going to do that by plotting some. Okay, so in order to graph the equation, we see that we have come up with a set of points based on various t values. Remember, t is your time. So we have chosen t values that range from 0 seconds to 3.5 seconds. And we've done it in increments of half of a second. So we've done 0, we've done a half second, we've done 1 second, we've done 1.5. Now, the x and y values come from the equations that we just derived. So I'm going to go ahead and just maybe select one of these and just kind of walk you through where those values came from. So let's look at the place where t is equal to 1. So I'm going to take my equations that I came up with just a minute ago. So we started with the y. And the y equation looked like this. And so what I'm going to do is I'm going to plug in a 1 everywhere there's a t. And if I do that and then type that into my calculator, I'm going to get for my y value 37.2. And similarly, if we take our formula for the x, which was x is equal to 137.9 times t, and we plug a 1 in for the t, we'll get as an x value 137.9. And you can see that these are the points that we came up with for the x and the y. And so now all we have to do is actually plot those points on a graph. So once we plot the points and we connect them, we can see that we have this smooth curve that looks like the graph on your screen. And this shows us the motion of that baseball after it's been hit. Okay, so let's move on to the kind of the second part of the same example. Suppose the ball in example 1 has been hit towards a 10-foot high fence that is 400 feet from home plate. Will the ball clear the fence? Okay, so our 400 feet is our horizontal distance. That's how far we are from home plate. And so our horizontal distance is our x. So this 400 feet is the x value. And we're talking about a 10-foot high fence. So the height of the graph is going to be the y. And so we can go back and kind of look at our graph and try to determine whether we think this is true or not. We can look for an x value of 400, which is going to be here, and a height of 10. And it looks like we're going to be okay. But what we want to do is we want to go in and algebraically calculate that just to be on the safe side. All right, so we know that the x value is 400, so let's work with that first. So if my x value is 400 and the formula that we came up with for x is 137.9 t, let's figure out the time that goes with this. So I'm going to put these two together and I'm going to plug the 400 in here for the x. And now I'm going to divide both sides by 137.9. And so that gives me a t value of 2.9 seconds. So we know that when we're talking about this ball at 400 feet, that the ball has been in the air 2.9 seconds. All right, so now let's look at the height at that same time. So I'm going to take my formula for height. That would be the y formula. And I'm going to plug in 2.9 seconds. And this is going to tell me the height at that particular time. All right, so again, I think the best way to do this is just to type it in your calculator at this point. So we'll go ahead and do that. And when we calculate it, we come up with a height of 14.02, so roughly 14 feet. Okay, so what does this tell me? This tells me that at 2.9 seconds, that the ball has a height of 14 feet. And so the question is, will it clear that 10-foot fence? And so yes, the ball will clear that 10-foot fence because the height of the ball is 14 feet. All right, and so we can go ahead and answer yes to this question.